Welcome to FormNext 2020. Ingersoll Machine Tools would like to present MasterPrint and how to choose the ideal applications for large format additive manufacturing. Hi everyone, I'm Curtis Gofinski, Principal Technologist at Ingersoll Machine Tools. I've spent my last 10 years at Ingersoll designing and commissioning advanced manufacturing solutions from large-scale milling machines to large format 3D printers. The MasterPrint large format additive manufacturing technology feeds a screw extruder with a pelletized thermoplastic feedstock. The extruder melts plastic into beads and layers. For stability and strength, the plastic pellets are often pre-mixed with chopped fiber reinforcement, be it carbon fiber, glass fiber, or even biofill like wood flour, flax, or bamboo. Here you see our development center machine in Rockford, Illinois. This machine has 4 meters between columns and 2.2 meters under the print head, though we often make machines much larger. On the right, you see the machine is equipped with 2 modules, first a print head, and second a 5-axis milling module. We've also developed MasterPrint Continuous Filament, which uses a continuous carbon fiber filament and a high temperature thermoplastic to lay complex paths. I won't go into great detail here, but the MasterPrint Continuous Filament is a high accuracy platform well suited for thin-walled diffusers and nozzles or reinforcement and overprinting onto existing parts. To paint a complete picture of the large format additive production process, I'd like to go over some of the process steps. We start with design for additive, where the part is designed specifically for what the process is capable of. Move into path planning, or the CAM job, which is often called slicing. Eventually the G-code is produced and machine motion is simulated for safety and accuracy. The process parameters are decided on the machine on the production floor, and the print is produced. Finally, post-processing improves the surface finish and dimensional accuracy, and the quality assurance phase certifies that print and tests it to production standards. Because additive manufacturing is still a maturing technology, and additive manufacturing in the factory, or large format additive manufacturing, is a younger still subsegment of that, it's helpful to apply the Gardner hype curve, which charts the expectations or hype of an emerging technology over time, from a sort of big bang disruption through the maturity of that technology. I like to think of this hype curve and technologies charted along it as time after a sort of big bang disruption, where we launch our expectations above an ideal adoption asymptote, where the area under the curve above this asymptote is high expectations resulting in wasted resources, and the trough of disillusionment below this asymptote becomes an unrealized potential. I would argue that while the consumer space may behave as an underdamped system with overshoot and undershoot, that heavy industry is more of an overdamped system, usually citing established supply chains, some lag of infrastructure, and security concerns. So to get to that asymptote faster for ideal technology adoption, we should get smarter at choosing the ideal applications for the technology. The standard way of doing this is a decision matrix. The old adage being fast, cheap, or high quality, we get to pick 2 of those. Here I've added a few additional categories, from competitive lead time or competitive cost, service temperature of the printed product, the geometric complexity of the print and final product, requirements for vacuum integrity as often pertains to printed tooling in the large format AM world, and then finally the dimensional tolerances. Recently, Ingersoll has used a decision matrix like this to analyze past, present, and future applications to determine their difficulty and their risk reward. We'd be happy to meet with you and go over your application in particular. I'll show some of those past projects here very quickly. A few applications were related to a fan cowl and composite tooling to create both the panel and the omega stringers. Using the MasterPrint robotic, we successfully printed the female mold for layup out of ABS 20% carbon fiber within 1 week using a few iterations of the design. And we also created some male forms to be used as tooling plugs for that panel, as well as male forms or tooling plugs for the omega stringer forms, the 3 unique forms there. We've produced some jobs for scale test tank testing for the marine industry. And here you see a 45-degree slice and print strategy that we used for that test tank job in order to print horizontal surfaces and long surfaces without any infill requirement. Very demanding application is aerospace layup and cure molds. This is a winglet tool printed using a standard vertical print strategy, and a room temperature tooling application for concrete casting. Utilizing an over 6-meter machine at the University of Maine, we printed a life-size 5,000-pound boat for demonstration. And also on that machine for the U.S. Army Soldier Center, a lightweight and rapidly deployable shelter system. As a quick summary, you see these project scores here with some of the room temperature, either casting or demonstration molds receiving the most feasible or easiest scores, whereas the high temperature, aerospace, cure tools, these types of projects receiving the highest scores. We'd love to go into more detail with you in a separate meeting or discuss your application and where it falls on the decision matrix for feasibility in more depth. So when we say that additive enables certain technologies or enables a process development, we mean that because it bridges the gap between talking the talk and walking the walk, where some in-stock raw materials can generate products fast that you can have in your hand and on your engineering desk or on your shop floor as quickly as possible, and bridge that gap between the computer simulation and having the tooling on hand ready to make a demonstration product. So to close the loop back to the Gardner hype curve, I would argue that printing end-use parts with large format additive manufacturing is yet to find its trough, while large format tooling is currently climbing up towards the ideal adoption. To wrap up with some background on Ingersoll, we're headquartered on our main campus just outside of Chicago, Illinois. We enjoy the support of our much larger Italian-based COMPOSITE group, but in the US, in Rockford, we have multiple services and products being developed under one roof, from assembly of new machines to a production and contract capacity, as well as our development center where we are developing and advancing large format additive technology. We have a long history of producing large milling machines and parts for various heavy industries, from wind to aerospace and even the large components of our own machines. And we are also world leaders in manufacturing large automated composite structure manufacturing machines. Here shown one machine with many modular production end effectors under one 9-meter between column gantry with some extended travel, and here a 4-meter z-axis travel, this being the world's largest composite production gantry. Thanks for listening to our introductory presentation on the suitability of different applications for large format additive manufacturing. Please reach out to us at FormNext for any additional questions on MasterPrint or our other machine platforms. We'd be happy to answer your questions or evaluate your specific application.